So, welcome to this new course on classical mechanics, and when you say mechanics, we have varieties of mechanics. Some of them I can write here. You have classical mechanics, then you have quantum mechanics, then you have statistical mechanics, so varieties of things are there. Classical mechanics, which is the topics from classical mechanics that we will be doing. So, classical mechanics is the one from which we will be doing this course, some of the topics. This is basically, it talks of particles and systems which are not very small, not in angstrom level or nanometer levels. So, quantum mechanics is the branch where we talk of small particles. Small particles. Not that here we will not be talking of small particles. We will, many times we will take examples where electron is going and proton is there and so on. But basically, if you want to understand the dynamics, the behavior of particles, then you have to go to quantum mechanics if the particles are very small means in the nanometer angstrom regions. But if you have micrometer type dust particle, starting from dust particle let us say, and then planets, okay. So, all that that range is governed by this. So, not too small, not too small particles. And you have yet another thing which is called relativistic mechanics, relativistic mechanics. So, the varieties of mechanics, this is the one where we talk of high speeds, and not always high speeds, many times the speeds are not very high, still you need this relativistic mechanics. For example, when you have fission or fusion of particles, nuclear particles, the speeds are not very high. A neutron with a very small velocity enters uranium 238, makes it uranium 239 and then it splits. That does not come under classical mechanics. These rules will not be able to explain all that phenomena. So, you do need their relativistic mechanics and quantum mechanics. Okay. Relativistic mechanics, that gives me how much energy will be generated, how much mass will be decreased, whether mass is converted into energy, those things will be here. Then quantum mechanics will be there, because we are talking of nucleus which is femtometer size, not even angstrom, femtometer size. So, combinations are needed. All right. So, this is it, and this statistical mechanics is when you have large number of particles, very large number of particles, and each particle has a different behavior. Here also we will talk very large number of particles, because we will be talking of rigid bodies, for example. So, rigid body will have a large number of particles, but then here you have like gas molecules in a gas jar. So, you have large number of molecules, each molecule is going in a different fashion. So, that is done under this statistical mechanics. Now, coming to classical mechanics, which talks of particles, system of particles, rigid bodies, like that. Here also you have three formulations. One is the mechanics, classical mechanics, formulated by Sir Isaac Newton. This was sometimes in 17th century, sometimes in the year, let us say around 1687 Perhaps this was the year when Newton published the mechanics book Principia. So, this is the roughly 17th century later half. This is the period when Newton formulated this. We call it Newtonian mechanics, where the central thing is force and motion, force related to motion. This is the central idea. This is a central area. We talk of forces acting on particles, exerted by other particles. So, forces are there, forces are causing motion, and from there this entire mechanics is developed. We will talk of various parameters like momentum, angular momentum, energy, all those things will be there, but basic central theme is force and motion. Then about 100 years from here, you have another formulation of classical mechanics which is called Lagrangian mechanics. So, the scientist was Lagrange, and this was around 100 years down the line, somewhere around say 1780s or so. So, here he was a mathematician basically, and he developed a total branch of calculus where some small variations are the key elements, and then some kind of least square or action principle and so on and so forth. So, that was the kind of mechanics which is equivalent to this Newtonian mechanics as such, because you can always go from here to here, but then the entire formulation is very, very different. And something around 50 years from here, you have another one which is Hamilton. This scientist is Hamilton, and the mechanics which he developed is Hamiltonian mechanics. So, these are all equivalent, but then the formulations are very, very different, and you have advantages for this one, you have advantages in this one, you have some advantages in this one. The biggest advantage of this Hamilton, this is basically the central thing is energy, kinetic energy, potential energy, some total mechanical energy. That is the central idea. Here the central idea is yet another function called Lagrangian function, again based on potential energy and kinetic energy, but totally different combinations. So, this was let us say 50 years from here, somewhere in that era, okay, in that era. So, this is how the very important thing and very interesting thing is that this formulation of classical mechanics can be used to very easily make this transition to quantum mechanics. Okay. So, although the classical mechanics and quantum mechanics, the rule are very, very different, but from this particular formulation, the structure is such that you can, if you have mastered this, then the mathematics of this quantum mechanics is very, very at least is related, connected. So, you can go from here to here. So, these are the kind of things that we do in the name of mechanics and then in the name of classical mechanics. In this particular course, we will be talking of this Newtonian mechanics, right. So, we will be talking of a single particle system, and then the forces acting on a single particle system, and then how it moves. And you all know that it is governed by 3 laws of Newton: first law, second law and third law. And then there are very well structured equations, F is equal to ma. You solve them to get the future of that particle. Once you know the initial, the present of the particle and the forces acting on them for each instant to come, you can predict the whole trajectory of that particle. So, single particle system. Then we will have a multi-particle system, several particles moving with respect to each other, and then once again how these forces will govern that. You will have forces between the particles by one another, you will have forces from some other particles which are not part of your system. So, how that behaves, then we will have all that rigid body and all that. So, this is the kind of thing the syllabus is given, or the topics which we will be covering here are given at the website in the opening page. Okay, so that is our focus, and let me start talking of Newton's first law, second law and third law. So, you all know, you had been studying this from high school time. Newton's first law is, if there is no force on a particle, the particle stays at rest or it moves with a constant velocity. So, in varieties of ways you can state the same thing, but essentially that is the first law, that if the force on a particle is 0, if the force on a particle is 0, then the acceleration is 0. Then the acceleration of the particle is 0. Essentially is this in a nutshell, because if it is at rest and remains at rest, that means acceleration is 0, or it moves with a constant velocity in the same direction, same speed, that also means acceleration 0. So, if you are talking of a particle, if the total force on the particle is 0, then the acceleration should be 0, and vice versa also. This, if acceleration is 0, right, if acceleration of a particle is 0, then according to Newton's first law, you can always say that the net force acting on the particle is 0. So, both ways, both ways. So, that is Newton's first law. Let us first talk of this, Newton's first law. No force, no acceleration, that is Newton's first law. But that is not always true, that is not always true. If I am in a rotating frame, or let us say I am in a car, accelerating car. So, if I am in an accelerating car, right, it is accelerating and I am sitting here, somewhere here on the seat, okay. So, I am sitting here, and then from the car's body some pendulum is hanging, right, some pendulum is hanging. What I see? I see that the pendulum, the string does not stay vertical, it makes some angle theta with the vertical, all right. Now, if I think of this particle, this bob of the simple pendulum, what are the forces? The forces are its weight mg and then the tension T. These are the two forces, because force is always exerted by some object, right. Force is by some object on some other object, that is how the force is conceived. So, the earth which is attracting everything, so it is also attracting the bob, and that force is mg in the vertically downward direction. And then other than the earth, the only thing in contact is this string, and string always exerts force along its length, string always pulls, and therefore, the force on this bob by the string is in this particular direction along the string. There is no other object which exerts force on this, and these two forces are not equal and opposite, and they will not add to 0. So, you have a net force, force is not 0, but what I see? I see that it is at rest and it remains at rest, okay. So, the acceleration is 0 for this observer here. If he puts the origin here, x, y, z axis, no coordinate is changing with time, x coordinate does not change in time, y coordinate does not change in time, z coordinate does not change in time. So, it is at rest, it remains at rest, acceleration is 0. So, force is not 0, but acceleration is 0. So, that means this rule that if force is 0, then the acceleration is 0, and if the force is not 0, then the acceleration is not 0, that rule does not hold here. And if you have a resultant of these two, and if you want to make force 0 and apply a force here, you apply a force here, you pull it, you hold the bob and pull it. Why? I want to make the force 0. This tension here, this mg here is giving me some resultant, and I apply a force to make this force, total force 0. What will happen? What will happen? This bob will be accelerated towards me. If I pull it, the bob will be accelerated towards me. So, F is 0, but A is not 0. Newton's first law is not valid in this frame, or if I am in some kind of a rotating frame, I am on some disk, and there on the disk I have put my x, y, z axis, then also this does not hold. So, Newton's first law is not a universal law as such, because we are always free to choose our frames of reference. Whatever is suitable for me, I will use that frame of reference. So, for some frames of reference it holds, for some frames of reference it does not. So, essentially what this Newton's first law is doing, it is defining or it is classifying that okay, there are at least some frames in which this holds, and we call them inertial frames of reference. We generally live on the earth, whatever we do, our activities generally because the technology is advancing very fast, and we are going to in spacecrafts to other places, the moon and Mars and all those things, but most of the time we are on the earth, and therefore a very suitable frame of reference is earth, and that is not inertial, that is not inertial. Now, no one can compel me that no, do not use the lab frame, do not put your x, y, z axis in the lab, and you have to go for an inertial frame, first search it, put your x, y, z axis there, and then do all the physics, all the mechanics, all the dynamics. That is not the way science goes. So, I am always free to choose my frame of reference, and if it suits me, I can use this frame or some other frame, whatever I like. So, this Newton's first law is essentially, it defines. Fortunately, the earth's frame of reference is close to inertial, although it is non-inertial, but it is very close to inertial. If you think of this condition that if f is 0, what will happen? The acceleration will be very small, exceedingly small. So, we can take it as inertial frame of reference, and if the acceleration of some object is 0, how much is the force? In the frame of earth, if I am there, how much is the force? How much the force needed to make the acceleration 0? That force is exceedingly small, and therefore we generally take earth as an inertial frame of reference, but whenever we want to do some physics where the accuracy is important and our instruments are sensitive enough to detect small changes in the motion, or we can measure very small forces, then yes, we do take care of the fact that earth is not inertial. So, this first law actually defines inertial frames of reference. And once the inertial frame of reference is defined from here, then we go to the second law. In an inertial frame, force on a particle, net force on a particle is equal to mass of the particle into acceleration of the particle. So, many times people say that, okay, why first law? From the second law, put A equal to 0 here, F will be 0, and that is the first law. So, first law can be derived from the second law. That is not very true, because this is also valid in an inertial frame, but what is inertial frame? That comes from the first law. So, first law has its own independent significance, and once the inertial frame is checked from here, then we say that, okay, in that inertial frame this will happen, and that is our Newton's second law. And then we have Newton's third law, which is very different from all this. It is called laws of motion. First law, second law, third law, these are called Newton's laws of motions, but the third law does not involve motion as such. So, if I talk of third law, okay, and that says that force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. I have written a long statement of Newton's third law. Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. Whereas the most popular version of Newton's third law is that action and reaction are equal in and opposite. But that short, the crisp, very simple, beautiful statement of Newton's third law, every action has an equal and opposite reaction, has caused a lot of confusion in the interpretation of Newton's third law, lot of confusions. So, basically the content of Newton's third law is, if you have two objects and they are exerting forces on each other, remember, for any force you can ask these questions: which object has exerted this force, on which object this force is exerted, okay? What is the magnitude, what is the direction, but basically from where the force is coming. So, which object is exerting the force and on which object it is being exerted. So, that is very, very important. So, if you have two objects, one is exerting force on the other is also exerting force on the first one. So, that is it, force by particle 1 on particle 2 and force by particle 2 on particle at any instant. This is also very, very important. In an action reaction statement, it appears that first some force was exerted, which is action, and then reaction also occurred. So, it is in reaction to the first force, the second force is exerted. It is not that, it is at any instant, at one single instant this is exerting force on that, at the same instant this is exerting force on this one. So, which one is action and which one is reaction has no significance, absolutely no significance, because at any instant, at one particular instant, this object is exerting force on this and this object is exerting force on that, and the two are equal in magnitude and opposite in direction. So, that is Newton's third law. The motion is not involved as such here, but how the forces are related. Here also there is yet another thing which we can add here in the Newton's third law, that and are these forces along the line joining the particles. This also you can add. If you have a particle here A, if you have a particle here B, the force by A on B and force by B on A at any given instant are equal in magnitude, opposite in direction, but that could have been this way. That could have been this way. The directions are opposite. The magnitudes are equal. So, this statement is satisfied. But the other part which you can add is that no, the force is along, these forces are along the line joining these two particles. Okay. Now, if that does not happen, maybe in some cases if it does not happen, then this part will not be valid. Now, if you stop here, what is Newton's law? Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. This, if you stop here, this is sometimes called weak form of Newton's third law, right. This is sometimes called weak form of Newton's third law. And when you add this also, that the two forces are along the line joining the particles, this is sometimes called strong force, strong form of Newton's third law. Okay, so we will stop here and we will talk further on forces in the next lecture.